So this is an introduction to LS-DYNA tutorial, and myself, I'm Anjani, and we'll be discussing only the basics of LS-DYNA. Since there are two tutorials, today we'll be discussing only a basic problem, which we'll be discussing using LS-DYNA, which is a static problem. We'll not go into blast load or blast response or anything today. uh, try to I'll try to explain about the solving a basic static problem. So before that, just an introduction to LS-DYNA. So LS-DYNA is an advanced multiphysics finite element software, which is developed by Livermore Software Technology Corporation, and now it is acquired by ANSYS. So now it is under ANSYS, and it can solve explicit and implicit calculation. Even though like both explicit and implicit is there, the key potentiality of the software LS-DYNA is in performing highly nonlinear transient dynamic finite element analysis, which are basically blast and impact, like high transient dynamic loads are blast and impact loading. And that's why we use LS-DYNA for getting blast or impact response specifically. And even though we'll be using all the modeling and all those part using a graphical interface, but LS-DYNA, the modeling and everything can be performed using a text editor also. And the image you see here is a response obtained using LS-DYNA for a column, which is subjected to a blast. Yeah, about this column response. I was telling this is a LS-DYNA response obtained using LS-DYNA. And for this, a blast charge is kept at a standoff distance of 2 meter at the mid height of the column. And the blast charge is around 200 kg. So you can see the response, like this is how we obtain a typical response for a column using LS-DYNA. And now I'll just briefly explain about the basic basic terms that we'll be using in LS-DYNA. Just a brief introduction. I'll not go deep into the theory or anything because it will take too much of time. So first one is section property, and in LS-DYNA, every properties like every parameters that we are assigning to a model, we'll call it as a keyword. And the section that I have shown in this bracket is actually a presentation of keyword, like with asterisks. We write this one, and then you can understand that it is a keyword in LS-DYNA. So here the section is actually uh, section, it defines the element formulation. The keyword section, it defines the element formulation and cross-sectional properties of the model. Element formulation is basically how you are performing the numerical integration. You know about this Gaussian integration rule. And you have studied about fully integrated and partially integrated elements. So in LS-DYNA, using section property, we tell the model, we tell the software how you want to perform the integration. You can perform either using single integrated elements or by using fully integrated elements. And in LS-DYNA, by default, for a brick element, we use a single integration option because single integration is very like it doesn't take that much of time. It like we can get the results very easily. And next one is material model. Material model is basically the constitutive equation, how your stress and strain going to respond. And the material model, when you when you give the material model keyword, you need to assign the material properties as the input parameter. And today and tomorrow for the both tutorials, we'll only be using the steel material. So I just gave a here I have given a few commonly used material models for steel, which are material plastic kinematic and material piecewise linear plasticity. And next is meshing. Of FEM, we all know element size is like it determines the accuracy of your solution. And people usually select element size based on the convergence of the solution. Like they perform mesh sensitivity analysis. They perform analysis using different mesh sizes like 25, 15, 10, and find like which gives the most accurate results. So here, usually a 25 mesh is like it gives a reasonably well result. So here I have just shown a 4-noded shell element and an 8-noded brick element, and these two elements we'll be using these two elements. And next is boundary condition. We all know in finite element method we provide boundary at the nodes, and for a column or like any structure if you take, you provide at the support like nodes at the support of that particular structure you provide. So here I have just shown a fixed boundary condition provided at the bottom of the uh, brick element. Fixed boundary, you restrain all the translation and all the rotations of this particular node. Next is load application. Load application we usually perform using defining a load curve. Like you define how your loading is done for the time duration. So you provide X and Y data where X will be your time and Y will be your load application. So here I have just shown two representation. One is static load, where you provide as a ramping load, and then you just maintain that load for some time, because if you just suddenly drop this, like stop this loading, it might create some numerical issues. So we'll just keep static loading in LS-DYNA, we keep it like that. And next is dynamic loading. And dynamic loading, this is just like idealized blast load. We represent as a triangular pulse load. So today we'll be using this static load curve. And next is output control. In LS-DYNA, you have to tell the software uh, at what interval you need your outputs, like what is the time step at which you need your response parameter, your stress and strain, at what locations you need your stress and strain, and all these things you have to provide to the software, then only you will get the response at that particular point. Next is the solution control. Solution control, we have to define for how long we need to provide this, we need the response. And also the for the explicit integration, we know it's a conditionally stable scheme. So we have to provide a particular, our time step should be limited, like it should be within a limit. And usually people select time step using this equation. L is the length of the element and C is sound speed in that medium. So these are the basic uh, uh, parameters that we will be discussing later in this uh, solution. So next I'll directly go to the problem and how to solve a solution I'll explain to you. And before that, I'll just provide you an outline of LS-DYNA analysis that I have already explained in the previous slides. First is a pre-processing. For pre-processing and post-processing, we will be using LS pre-post software, which comes with LS-DYNA, and it is very free, and it is free. I think you all have already downloaded and started like using the software. And in pre-processing, we define a solution control, output parameters, model geometry, material parameters, and then boundary conditions and loading. So once you provide all these details to the model, then we can run using LS-DYNA. And LS-DYNA, it solves the problem and it creates the results file. And the results file, you then have to post process using LS prepost so that you get the response parameter history like stress history, strain history, all this you can get, and you can get the blast pressure history from the LS prepost results file. Also the damage pattern that I have already shown you in the first slide itself, like how your column is going to damage. These all things you can obtain using post-processing. Next is regarding the units. So LS-DYNA, unlike other softwares like where we can provide, we can select a particular set of units, LS-DYNA does not have any unit system. So that we give the values so that it is in a consistent set of units. So general units, although we can use different set of units, usually we prefer using general units in terms like length in terms of meter, mass in terms of kilogram, time in second, pressure in Pascal, and all this, and mechanical units, kilogram per meter cube and Pascal. So you can provide units as an millimeter. Like there is another set of units which are like millimeter, gram, millisecond, like that. But you can never give units in like from different set. You cannot give, like you cannot provide length in meter and like you provide mass in gram. That you cannot do. If you're providing length in meter, you have to provide mass in kilogram, time in second. And if you're providing in millimeter, the correspondingly you have to change your mass, time, and all this unit. Otherwise, you will not get a accurate result. So next, I'll directly go to the problem statement. And we have a steel cantilever structure, and it is supported at one end it is fully fixed support, and at the other end we are applying a concentrated load of 18 kilonewton. So the dimensions of the structure is 1.2 meter length and 180 mm height and 10 mm thickness. And all the details are given in this slide. The support, material properties, everything is given so that later when you are trying to model this one, all the parameters that you require is in this slide. So this one will be modeling as a shell element because the thickness is very less and we don't have to model it as a beam element. Not beam element, brick or solid element. So the first step in modeling the LS prepost is that you open the LS prepost icon. So which you can see like as an LSPP. And once you open the LS prepost window, you can see this window as like different tools you can see. So in the top one, it is all the menus and it shows all the features and like you can change the geometry and you can like background and all these features are there. But you don't need all these features for modeling your problem. And this toolbar will not be using that much. And the main toolbar is on the uh, right side, which we'll be using extensively for modeling our problem. And you can see like what are the tools. You can see defining, these are all like meshing related. If you click on this one, you can generate different types of meshes. And the modeling, the model, it shows like you give all the material and all the model related parameters you give here. These are some element tools like copying an element or deleting or editing the element. These all things you can do using this element tool. And finally, the post processing. With post processing, you can obtain all this data, stress, strain, damage pattern, everything you obtain using this post processing. And finally, at the bottom, you can see a lot of tools. These are all related to the display rendering buttons. And here you can see like here it is like if you click on this mesh icon, you can see your model in a with mesh. And if you click again, that meshing will be like without mesh you can see. Then there are like wireframe model. These are all for like display of your model. shaded elements, everything is there. Like these are like not that important. And then again, you can zoom in or zoom out, auto center. And the important one is this one. So here you see a friend, like a button with friend, and here you can see an arrow. So if you click on this arrow, you can see like different um, viewing position, front view, back view, top view, isometric view. These view you will be using, like you need to use different views for editing the model and basically like to model the problem. And these are all with the window. So we'll go to the second step. Second step is just start modeling your geometry. So right now we have a model where you have a steel cantilever and we need to provide shell elements. So to create shell elements, you go to this keyword, the toolbar, right side toolbar I have shown you. Like here, you can see the mesh and element button. Once you click on that mesh and element button, you can see a shape measure, and there are like lot of other options, automatic meshing and 2D meshing. This is 2D meshing. So these different options are there. So right now we'll just focus on our problem and I'll show you how to explain, because if I start explaining all those things, you'll be like, that will be too much of information. So I'll just give you how to do the modeling for this particular problem. So you can go to shape measure, and once you open the shape measure, it shows a box. So in that box, it shows an entity. So in entity, you can see box solid. So basically, this is for modeling solid elements. And for us, we need shell elements. So just click on this arrow near to this box solid. So once you click, you can see there is a list of elements, and from there you select the foreign shell. Then after selecting the foreign shell, you get a particular dialog box in which you can enter the coordinates of your shell, your steel cantilever. So we start with 0, 0, 0, and since our length is 1.2 meter, next coordinate will be 1.2, 0, 0, and third one will be 1.2, and it is 180 mm height. So it is 1.2, 0, 0.18, and the final one will be 0, 0, and 0.18. So just keep in mind that we'll not be modeling the thickness of the shell right now. So for shell, we just provide the rectangular coordinates, and then in the section part, we'll provide the thickness of the shell. So that's how we model the shell. Also, here in the next one, you can see a next number, which is a number of elements in the x direction. So ours is a total of 1.2 meter, and we are providing 12 number of elements along the x direction, which will be like, for one element, we'll be using 100 mm mesh. And along the y direction, nx, ny is the number of elements in the y direction. And once you provide all these data, you just come down, you see the target name. So whenever you model a part or anything in LS-DYNA, you have to provide a name and target ID. So here you just provide, since ours is a beam, sorry, we'll name it as a beam and just provide a part ID as 1. And once you provide all these details, you just click on the create button. So when you click on the create button, you get a window like this, in which it will show the uh, like it will show the meshing, and here you can check like whether the number of more elements and the geometry is the way you want it to be. If it is not accurate, you can always reject the model. And if it is okay, your model is right and everything is fine, just accept it. And once you accept it, just click on done. Like you're done with the modeling, meshing of this geometry. So here I provided just what I've explained. I have just written here just the XY coordinate, target name, and everything you can provide, and then create. So once you accept this mesh, the window look like this. You'll have the shell element with 12 numbers of elements along the x direction and 5 in the y direction. So this is our geometry. So now you have the geometry. Now you have to provide the material properties for the model. And for defining the material property, we have to go again to the toolbar, right toolbar. Right toolbar, you can see again, we have already used the mesh, and below that you can see a model part. So if you click on the model, so this is the main toolbar, and if you click on any of these tools, you can see the subset for this particular tool. So if you click on the model part, here you can see the subset for this model tool. So here you can see a keyword option, and this we'll be using, or we'll be providing all our parameters, all the data and everything in this keyword manager. And when you click on this keyword, you get this box. So this and here basically you can see it shows model and it shows all. In model, if you select the model, it will show the parameters that we have provided to our model. And if you click on all, it will show all the parameters, all the like keywords that are available in the LS-DYNA deck. So here you just change the selection from model to all. So when you click all, you can see like this is the all selection. You can see all the keywords that are available in the LS-DYNA. And from this keyword, like you can see like whatever keywords you have already provided to your model, that will be shown in the blue color. So since we have already like developed the mesh, the number of nodes, and we have developed a part. So these nodes and part are already provided to the model. And then we have to provide the material properties. For that, you go down and you can see these are all in alphabetical order. So you can see after all, you can see the mat for keyword. Mat is for material. Then you can click on this positive sign. So once you click, you can see all the list of material models which are available in LS-DYNA. And these material models, they are provided in numbers, like they are provided a number. So our material model, which is plastic kinematic, is number 3. And then you can double click on this material model. When you double click, this box will come, and in that box, we provide all the material related data, which are first, you have to provide a title. Since ours is steel, we just provided a steel, and we have only one material model. So material ID will keep it as 1. And density, rho is density of the steel, 7850. E is the modulus of elasticity. PR is the Poisson's ratio. And sigma y is the yield strength of the steel that we are using. And E tan is the tangent modulus. This is a tangent model. This is for the bilinear. Like we'll be considering elastic and plastic stage. So E tan is for a bilinear tangent modulus for the bilinear curve we are providing. And remaining parameters we don't require. And once you provide all these parameters, you can just go here, click accept. So when you accept this one, your material, whatever material model that you have defined, that will come here. So we have one model, steel mode. And so here you require only one model of steel. But when you're modeling a concrete, you need different materials. Like you need concrete, then longitudinal and stirrups you have to provide in steel. So when you have to provide more than one number of a material, just click on add. So when you click on add, again this blank box will come where you can provide again the data for all this model and just accept. That's how you do for different material models. So now you have provided the material for the problem. Next one is the section properties. So again, you go to the section. This is your keyword, like the list of keywords that we have. So from this list, we have already selected the material. So next one is section. So if you click on this section again, you can see the list of elements that LS-DYNA has. Like you have beam element, shell element. If you go down, you can see like solid elements are also there. So for us, we need shell elements. So click on this shell element. When you click on the shell element, you can see like you have to provide the data. So if you remember, like when I explained about this section properties, told you like we need to provide the element formulation and the cross-sectional property. So here you can see you need to provide the title. So we just provide it as a shell. Next one is section ID. We have only one section, so provide it as a one. Next is the element formulation. So if you click on this element formulation, you can see like you can select which element formulation you need to use for your problem. And here we'll just take the default value. So element formulation 2 we will consider. Next one is a shear correction factor. We'll provide it as 0.833, and rest are all default values. We'll take all this as default values. And the next parameter that we require is the thickness of the shell, because we model our cantilever as a shell with only rectangle, like four coordinates. So the thickness of the elements are not provided. So here in T1, T2, T3, T4, we provide the thickness of the shell element, which is 10 mm. So when you provide all these details, again, go here, accept, and done. Again, if you have more than one section properties, you can add here. And if you have like beam properties, you can select from here and add that as also a section property. So now you have already provided the material model. Here you have provided the section properties. So now we have just provided the values for the section properties and the material properties, but we haven't assigned that properties, material or section properties, to the model that we have created. So the next step is applying the section and material properties to the part. So here again, keyword, you go to the keyword. So you can see here part. So since we have already, we have modeled the geometry, the part section will be in blue color. So if you go to the part, you click on this positive sign, and then you click on this part. And when you click on this part, this box will appear. So in that box, you can see again, title, we need to provide the title. Part ID is here. And here we just select the properties that we have assigned to the material and section. So here you can see in part ID, here it is section ID. So if you click on this black button, it will go to the list of section properties that we have provided to the LS-DYNA. So from there, you can select the one you want for your model. So here we have only provided one section properties, one section ID. So if you click on this one, you'll get a list in which the particular section ID that we have created will appear. You can select that one and then it will be automatically updated here in this section ID one. Again, material ID, if you go, the list of material properties that material models that we have assigned will appear. You select the material model that you want for this particular part and then you go here, accept and click done. So now we have a model in which we have provided the section properties like cross-sectional details and element formulation, material models, and everything we have already provided. The next one, we have to provide the boundary condition. So applying a boundary condition is it requires a few more sub steps. It's not as direct like we applied for section properties or material property. For that, you need to create an entity set for the boundary condition. An entity set is basically a set of entities. It can be nodes, it can be set of beams, it can be set of solid elements or like shell elements, or it can be any, like you can see the list here. So again, you go to the toolbar. When you click on this model, I told you like we get the sub tools here. First one, we took the keywords and we provided all the section material properties. And now we just go down and we click on this create entity option. CREENT is create entity. So when you click on this create entity, you get a box like this. So in that box, you can see a lot of options are there. But what we need is set data. If you click on the set data, it will show the entities like set node is the set beams are the set part, set segments, shell, everything is there. But we need to select the number of nodes for which we will be applying the boundary condition. So I've already shown that like at support, we select the number of nodes and then we apply the boundary condition. So here you go to set data, you click on the set node. So when you click on set node, this option will come in which you just select the create option. Show is just to show the number of entity, like what are the entities that you have already created. CRE is creating, then modifying your entities, deleting is all that. You just go and click on the create button. So when you click on the create button, a window will appear like this, in which you can select select the nodes using area. So click on the area option to select the nodes. When you select the area, go to one support of your beam and then select the nodes for which you need to apply the boundary condition. So these are the nodes for which we'll be applying the boundary condition. And once you select the number of nodes, go to the dialog box that have already like when we click on the set node, it will come. So just go here and click on apply. So if you click on apply, the entity set will come here. You can see our first entity set is nodes, in which 6 number of nodes we have selected. You can see here we have selected 6 number of nodes. And when you have already selected, you just apply and then done. Click on done. And so now we have the nodes for which we need to apply the boundary condition. So we already have the node. We just have to apply now the boundary condition for those particular nodes. For that, you again go back to the list of keywords. You go to the keyword and then you can see in the top boundary option is there. So if you click on the boundary option, the list of boundary condition which you can provide for the nodes is available. From that, you can select the SPC set. So in SPC set, if you take the SPC set, the box will come like this, in which you provide an ID and a title for the boundary condition. So I just provided boundary condition as top boundary. And here you can select the node set for the boundary, which is the node that we have already created. So here, when you click on this one, the list of entities will come, node entities will come. From there, you select the entity that you want to provide this boundary condition. So now we have selected the node set for the boundary. So next one is providing what boundary conditions we need for that nodes. So here we are providing a fully fixed support. Fully fixed support means restraining all the degrees of freedom. So here Fx, Fy, Fz, Rx, Ry, Rz is these three are translational degrees of freedom and these three are rotational degrees of freedom. We need to restrain all the degrees of freedom. So if you press on this one, you can see either a 0 or 1. If you click on this arrow, 0 means you are not restraining that particular degree of freedom. 1 is you are restraining that degree of freedom. So here we are restraining all the degrees of freedom. And suppose we need a pinned condition for which we'll be having restraint in the X and Y direction only. So for that, we'll just restrain the X and Y. We'll keep the X and Y as one value. And for the remaining all, we'll just keep it as a 0, which is like it's not in a restraint condition. So now you have provided your boundary condition. Next one is applying load at the free end. So we have an 18 kilonewton of load at the right end of the cantilever. So for that, again, defining for load application also, we need some sub-steps which are defining the load curve. So here again go to the keyword. You can see define option. In define, you can see the keyword curve. If you click on the keyword, you have to double click for all these things. Double click on the keyword. This box will come, in which again provide the title, provide the ID for the load that you are applying, and here you can provide the X and Y coordinate. So I told you, like in static, for the application of static loading, we'll just provide a ramping load, and then at the top we'll just maintain that load for some duration. So for that, the X and Y coordinate, initially it is 0, 0, and at 1 second of time, we reach to the peak value. And here we'll not provide the full force, will not provide. We'll just provide the history. And later when we are applying the load, we'll provide the scale factor. We just provide the load history here, and then the complete load will be applied during the load application. So here at 1 second, the load has reached to its peak value. And again, to maintain that force, we'll just provide one more coordinate, which is at 1.1, the force is again 1. And after providing, like here I have provided, after inputting one set of X and Y values, suppose you are providing 0, 0, then you have to click on insert. And then only you provide the next set of value 1, 1, and 1. Again, click insert, and again you provide 1.1 and 1. You click insert, and finally you accept. So when you accept, if you go to this plot option, you can see the load curve that you have defined. If you see any mistakes in the like the load curve, you can again come back here and you can edit the values, and you can like delete the values here. You can replace the values, and that's how you can edit your load curve. So now you have provided the history of your static load. The next step is applying that load to the model. So for that, you need to find, see, we need to apply the load at this point. For that, you have already defined the load duration, load curve for this point, but now you have to tell the software at what point you need to apply your load. So for that, this step is just to finding which node number you have to apply the load. So for that, you can go to element tool, and these are all like in the keyword you can see mesh model element tool. So if you go to element tool, this ident option is there. You can just click on this node using this option, and it will show the node number for that particular node. So once you get that node number, you can apply. Now you can apply the load. You go to the load, and here if you click on this positive button, you can see node point. So we apply as a point load at the node. So that we can apply using node point. If you click on this node point, you can see this box in which node ID we have to provide, which is the 6. Like in the previous step, we have seen that the node ID for this particular one is 6. So we just provide the node ID of 6. Next is degrees of freedom. So we are providing degrees of freedom in the vertical direction. So you select degrees of freedom 3 means it is in the Z direction. And next one is load curve ID, which is the load curve that we have already created in the using the define option. Like we provided a ramping load. So we select the ID, load curve ID for the ramping load. And here we provide the actual value of the load. So we are providing an 18 kilonewton load. In define curve, we just provided the history, and here we provide the scale factor. SF is the scale factor for the loading curve. So when your load curve, it reaches the one value, it is actually scaled by 18 kilonewton. And then you accept and you click on done. So now you have all the data that are required to solve the problem. So next one is all solution and output control parameters. So for that control option, you have to go to this control section, click on the icon. There are list of control options available in which you require only two control options. First one is termination. If you click on termination, termination is basically for how long you need your analysis to run. So since we have provided 1 second of duration of a load duration of 1 second, we'll run our model for 1 second. So here we can see end time, END time. It will show I have inputted as 1, and then click on accept and click done. Next one is the next solution control is the time step. So in time step, you just have to like open the time step and click on accept, because you can use the default values. These are basically for controlling the time step of your numerical integration. So just click the default, just accept the default values that are there and click on done. The next one is your output parameters. Output parameters is basically I've told you like in what interval you want your response to be printed. So here you go to database. We just provided control option. Now we go to database. In database, you go to binary D3 plot. So if you click on binary D3 plot, you get this dialog. Here, you just have to provide one value, which is the dt. At what time interval we need the response. So we just provide 0.01 because our total time duration is 1 second. So we need the response in 0.01 second. You provide the dt value here, click on accept and click on done. And so now you have provided all the parameters and input values that are required for the modeling of this particular problem. So once you model everything, you just go to next step is like saving your model. So you go to file and it's like common, everyone knows, like you save and then once you click on save, you just click the option save keyword. So LS-DYNA files will be represented in .k format. So you just click on save keyword and then you have to provide the location of the folder and everything that you can do that I have been included. And next step is finding the LS-DYNA solution. So for that, LS-DYNA, LS prepost you all can easily get because it's freely available. LS-DYNA, it's a licensed software, so you won't be able to run the software. You won't be able to run the model. So for LS-DYNA, this is the interface. So when you open this LS-DYNA program manager, you can see an option solver. So in solver, you just click on the LS-DYNA, start LS-DYNA analysis. So if you click on the LS-DYNA analysis, this box will come. Here you can select the file for which you have to perform the analysis. And you can keep all these things as default values and click on the run option. And once you click the run option, you can see a command window in which like this LS-DYNA, it will show all the running, like at what time it is printing, all these things it will show. And finally, if your analysis is correct, you can see a normal termination. But if your model is having an error or like incorrect input values or something, this analysis, the command will terminate and it will show an error termination. So if you are having a normal termination, that means your model is running properly. There is no error. Like there can be other issues, but uh, as of now, the model can run using LS-DYNA. And now the next step is post-processing your model. So post-processing again will use LS prepost, and for that you can open LS prepost again. Go to the file menu and select the open and click on open. It will show like LS-DYNA keyword, LS-DYNA binary D3 plot. From that you can select the LS-DYNA binary D3 plot. So if you click on the LS-DYNA the binary D3 plot, you can again see D3 plot which will open. And this will be the window that you'll be seeing after the analysis. So here, if you hit the play button, this model, it will show, it will render like how this model is going to deform and all these things you can see from this one. And again, if you have to see a more clear damage and like where the stresses are high, all these things you can do. For that, you have to go to the post processing, this post option, click on this post. It will show a list of subtools. Here you can see like fringe component, history variables, and all these things. You can obtain the response parameters from all these things. And you go to the fringe component, which will basically show the fringe plot of this different parameters. So if you click on this fringe component, you get a box in which the list of parameters are provided. Like you have X stress, Y stress, Z stress, and strain parameters, pressure, and all these things. If you click on any of these things, a fringe plot for that particular parameter you can see. So I've just clicked on the von Mises stress. So if you click on the von Mises stress, you can see the fringe plot for particular model. So the highest one being at the support. And next one is examining the results of LS-DYNA analysis, post-process results. So we can obtain the response history using the post-processing. So for that, again, you go to the post-processing icon. You click on the post, and then from the list of subtools, you click on the history variables. So if you click on the history variables, actually there is one more box, I have missed that. If you click on the history variables and you select the node from your model, you select a particular node or element from your model, and you plot the stress, X stress, Y stress, Z stress. You can plot all the stress and strain. You get a particular curve like this. So this is the X stress which is obtained for the particular model. And that's how you do a complete analysis. And